Right. So this is about the introduction about the refrigeration. The mechanisms used for lowering or producing low temperature. So we know what is refrigeration, why we are go with the refrigeration. So to produce lowering temperature, right? So in a body or a space whose temperature is already below the temperature of its surrounding is called the refrigeration system. So here the heat is being generally pumped from low level to higher level, is rejected at a high temperature. So this is the principle of refrigeration. Then the basic operations of refrigeration, and so the objective of this unit is, so we have to know the basic operations of refrigeration and the AC system, that is air conditioning system. Then we have to know the principal components of refrigeration and AC systems. Then we have to know the thermodynamic principles of a refrigeration cycle. Then the safety considerations of the both refrigeration and air conditioning. Then the generic refrigeration cycle will involve two parts. One is high pressure side, then we have low pressure sides. So we know what are the components we used in the other cycles. So like that we have the components: condensers, then compressors, then evaporators, then expansion device. So in this device we can classify that low pressure side, then high pressure side. So we can get the low pressure in the devices like compressors, then evaporators, then expansion device. Also we can get the high pressure with the components like compressors, then condenser and expansion device. So we can divide the cycle by two half. That is one is high low pressure side, then we can have high pressure side. So we can have what what is high pressure superheated vapor. Then we know what is high pressure subcooled liquid. Then we know low pressure wet vapor. Then we know what is low pressure superheated vapor. So we can divide that by 2. Then the actual refrigeration, the term refrigeration may be defined as the process of removing heat from substance under controlled condition, right? So we can define the refrigeration process. So it's also include the process of reducing heat, right? So it's also includes the process of reducing heats and maintaining the temperatures of the body below general temperature of its surrounding. So the main agenda of this refrigeration is to maintain the temperatures in low temperature, right? Then in other words, the refrigeration means a continued extraction of heat from a body whose temperature is already below the temperatures of its surrounding, right? So you can assume that so we want to maintain the temperature in a fridge, right? So we can able to see the commercial fridge available in your homes. So in that we want to maintain the temperature inside the fridge. So but the surroundings like our room temperature will be higher than the temperature inside the fridge. So this is the principle of refrigeration. So we want to give the continued extraction of heat from the body, right? Then so there are a lot of methods for producing refrigerations, so that were stated here. So we can have sensible cooling by cold medium like so ice. So ice is already a cold medium, so we can use the ice to get the refrigeration. So these are the examples. So cooling of right, so cooling of fish with ice also possible to get a refrigeration. Then cooling with the cold air or cold water or brine. So you can search the what is an use of brine. So the brine is a cold medium, like air. The brine also a cold medium. So this brine is used to get ice in ice factory, right? So actually these are cooling already cold medium like or ice, right? So there is one possibility with the to get the refrigeration, that is sensible cooling by cold medium. Then also we can get the refrigeration by endothermic mixing of substances, right? So it is possible to get the refrigeration with the endothermic mixing of substances, that is refrigeration effect obtained by a obtained in is small. So here we can get the some amount of refrigeration effect alone. So there is possibility to get the refrigeration with the endothermic mixing of substances. Then we can have the phase changing processes such as sublimations, then melting and operations. So to get the refrigeration. So the third possibility is phase changing process. We know what is sublimation, then we know what is melting and evaporation. Then the melting of ice produces a refrigeration effect in the surroundings, that we know. So only we can melt the ice. So because of that we can produce the refrigeration. Then the expansion of liquid also will produce the refrigeration. So that is a popular method of cooling used in the refrigeration system. Then we can have the isentropic, then isenthalpic processes. So to get the expansion of liquids, right? So that will produce our refrigeration. Then we can have the another method, that is expansion of gases also possible to get the refrigeration. Then we can have the another magnetic refrigeration also possible, that will be adiabatic demagnetization. Then there is another method, thermoelectric refrigeration. It is based on the reserve feedback effect. So we no need to discuss much on this. So just we are going to look at the endothermic mix, these phase changing processes, right? So before we are look at the components of the refrigerations, we want to know what is COP, that is coefficient of performance. This is actually a comparison of efficiency. So in efficiency we will denote that by a percentage, but in a refrigeration system we will get the percentage by more than 100%. Because of that they introduce the word coefficient of performance. So we can have what is coefficient of performance is a measure of efficiency of a refrigeration cycle system. So it is the ratio of refrigeration effect to the energy spent. So like our efficiency, so we know what is the formula for efficiency, the output by input, right? So like that we can have the COP as a refrigerating effect to the energy spent. That is, we can have the output as a refrigeration effect and we can give the input as energy spent. So the COP is same as efficiency, but right. So refrigerating effect is the amount of heat removal or absorbed from the substances to be cold. So this will be our output. Then the energy spent may be in the form of work in that is vapor compression refrigeration system, or heat in vapor absorbing refrigeration system, right? So we can have two types of refrigerating system. So if that is in that is the system is vapor compression refrigeration system, we will give the input as work. If in the case of VAR, we will give the heat as the input. So we will look at what is VCR and VAR in the upcoming slides. So the thing is, we can have COP as a output by input. So here output is refrigerating effect and input is energy spent. So if the work is given, we can have the vapor compression refrigeration system. If heat is given, we can have the vapor absorbing refrigeration system. And we can compare the both COP and efficiency. COP indicates the effectiveness of a refrigerator or heat pump. So if the terms refrigerator or heat pump is came, so we have to use the word COP. For refrigerator, the desired result is extraction of heat from space, right? So that is output, right? So the output will be extraction of heat from space. Generally, the value of a COP of refrigerator is more than unity, right? So we will get the efficiency as a percentage, that is in unity, but in the term of COP we can get the more than unity, but the value of efficiency is less than unity. So because of that they introduced the word COP. So it is for the these reasons the term COP is used for the rating of refrigerator, also heat pump. Then so these are the schematic diagram will show you the refrigerators and heat pump. So in the first figure, we'll give you the refrigerator diagram. Then the second diagram, we can have the heat pump. So the thing is the same, but the components involved in these two will be different, right? We can look what is refrigerator and what is heat pump. So the transfer of heat from low temperature region to high temperature one requires a special device called refrigerator, right? So the thing is we have to transfer heat from low temperature region to high temperature one, right? So then another device that transfer heat from low temperature medium to high temperature one is heat pump. So the thing is both the refrigerator and heat pump is same, but the process. So here we have to transfer heat from low temperature to high temperature region. But where in the case of heat pump, again this will transfer heat from low temperature medium to high temperature one. So refrigerator and heat pumps are essentially the same device, right? So they differs in their objectives only. So we can get confusion with these definitions. So the objective of these two is same, but the objective of the definition of these two will be same, but the objective is different, right? So we will look what is the objective of these two. So in refrigeration of the COP of refrigeration, we can have the desired output by required input. So in refrigeration, the desired output is cooling effect. So we have to get the cool. But where in the case of a heat pump, the desired output is heating effect, right? So the principle is same, but the objective of these two is different. So if you want a cooling effect, we can go with the refrigeration. If you want heating effect, we can go with the heat pump, right? So if you can differ the formulas also. So QL by W net will be your COP of refrigeration. Then QH, heat transfer with the high temperature. Then this one heat transfer with the low temperature. Then by W, right? So just we can refer the diagrams. So the refrigerator is used to get the cooling effect. Then heat pump is used to get the heating effect. So this just we are removing this heat inside the refrigerator. Then we are sending that to surrounding. Then where in the case of heat pump, just like refrigerator, just we are from the cold environment, just we are taking the latent heat. Then we are passing that latent heat to the warm house. So then we can get the house warm. So in the both the case, we need to give the W like your input. Also, this will be your output. This will be your output. So this is required output. Then where in the case of heat pump, that QH will be your output. So based on that, we can differ the refrigeration and the heat pump, right? So we can also simply say the objective of refrigerator is to remove heat from cold medium, and the objective of a heat pump is to supply heat to a warm medium. Like so, if that is in the case, then we can compare the COP of both. That is a COP of heat pump will be COP of refrigeration plus 1. So for a fixed value of QL and QH, the terms applied, the conditions applied. So if the QL and QH is fixed, then we can compare the COP of HP is equal to COP of refrigeration plus 1. So right, so before entering the refrigerant, we can compare the refrigerator and refrigerant. So refrigerator is a reversed heat engine or a heat pump which takes out heat from a cold body and delivers it to a hot body, that you know. The refrigerant is a heat carrying medium. So this is a refrigerator. We know refrigerator is a device. So we can transfer heat from cold medium to high medium, right? So the refrigerant, the term refrigerant is a heat carrying medium which during their cycle in a refrigeration system absorbs heat from low temperature system and delivers it to higher temperature system. We know this refrigerant is a medium like air, then our steam that we already discussed. So refrigerant also a medium, so used in the refrigerator, right? So we can also see the unit of refrigeration. The capacity of a refrigeration unit is generally expressed in tons of refrigeration, right? So the rate of removal of heat in cooling operation was expressed in terms of kilograms or tons of ice required per unit time, usually or a day. So we can have the unit of refrigeration, that is ton of refrigeration, right? Right. So if you want the rate of removal of heat in a cooling operation, we can state by the kilograms or ton of ice required. Right. This is a unit. Then uses of systems. The uses of this refrigeration system is the cooling of food stores and cargo. Then cooling of electronic spaces and equipments. Then we can have CIC, computers and consoles. Then we can have the system for cooling radio, the communication gears. Then radars also cooled by the system. Then sonars also cooled by the system. Then the another part, air conditioning for a crew comfort is used. We know. So we can have both refrigeration and air conditioning. So before use of these two, we have to know the principles and the thermodynamics involved in these two systems. Yes. So this is your typical refrigeration cycle. So in this refrigeration cycle, we have the components: compressor, then condenser, then this is valve, then we have chiller. So receiver is there, compressor is there, condenser is there, then chiller will be there. So these are the components of our refrigeration cycle. So in that we can have the low side, low temperature side, then we can have the high temperature side, also high pressure side. Right, so we will look that in the upcoming slides one by one. So the refrigeration cycle, in refrigeration system, the heat is being generally pumped from low level to higher one and rejected at a high temperature. This rejection of heat from low level to high temperature can only be performed with the help of external work according to the second law of thermodynamics, right? So we are involving work here, so that will be comes under the second law of thermodynamics. So then only we can transfer heat from low level to high level. But the general principle of heat transfer, the heat can only transfer from high level to low level, that you know very well. But if we want to transfer heat from low level to high level, we want to give work as an input. So that is the principle of refrigeration cycle here. Then the total amount of heat being rejected to outside body consists of two parts, that is heat extracted from the body to be cooled, then the heat equivalent to the mechanical work required for extracting it. So we need to know the two criterions, that the heat extracted from the body is to be cooled, right? Then the heat equivalent to the mechanical work required for the so we want to know how much amount of work is required to get the to extract the heat from the body, right? So these two are the principles in the refrigeration cycle. So then These are the types of refrigeration. So we can have VCR, then we can have VAR. Also, magnetic refrigeration cycle is possible. Then we can have industrial refrigeration also possible. So we know what is VCR. So vapor compression refrigeration system is stands as VCR. So uses in mechanical energy. So we will use work as a input to this VCR, vapor compression refrigeration system, where in the case of vapor absorption refrigeration system, the thermal energy is used as an input. Right. So also we can have the other types like magnetic refrigeration, then industrial refrigeration. So in this magnetic refrigeration, they remove heat and maintain low temperature is by the magnetic effects. Then also we can have the industrial refrigeration used in cold storage. So these are the types of refrigeration. But in our syllabus we can have only the VCRs and VAR. So we will look that. So the first type is VCR, that is vapor compression refrigeration system. So the overview of VCR is highly compressed fluids tend to get colder when allowed to expand. Right, that we know very well. Just we have seen a lot in steams. So if the steam is allowed to expand, so we can get we can remove the temperature. So the highly compressed fluid tends to get colder when allowed to expand. So thing is, we have to allow the refrigerant in the form of highly compressed is allowed to expand. Then we can get the low temperature in that refrigerant. So if pressure is higher enough, so we can use that in this. If the refrigerant is highly compressible, we can use that refrigerant to get the VCR. Then the compressed air hotter than the source of cooling. Then the expanding gas cooler than the desired cold temperature. So these are some overview of that VCR. So the advantage of this VCR, a lot of heat can be removed. A lot of thermal energy to change liquid to vapor is possible. Because of that, we can remove a lot of heat from the system. Then heat transfer rate remains high. So in this VCR system, because of that, we are going with that. So temperature of working fluid much lower than what is being cooled. So the medium, the refrigerant used in this VCR will give you the high heat transfer rate high. So we have the type of refrigerant used in the VCR, that is chlorinated CFCs, that is chlorinated fluorocarbons. Then also we can have freons, that is R11, will be in this VCR refrigeration system. So these refrigerants are determined, but the required cooling temperature is important in this. So because of that, we are using CFCs and R11 in this VCR system. So there are a lot of refrigerant available. So mainly we will use CFCs and R11 in this VCR refrigeration system. So this is our actual vapor compression VCR cycle. So in that we can have the compressor, evaporator, expansion valve, condenser, then gas engine. So you know why we need gas engine to get the compression, to get the refrigerant get compressed. Then so we can get, so you know, yes, you know what is the function of compressor. Then you know what is the function of condenser, that we already discussed a lot in the previous units. So compressor, the main purpose of compressor is to get to compress the air, to increase the pressure of the air or whatever the medium. Here in the case, we will use the refrigerant like R134A. So we can have the lot of refrigerant, so that the compressor will get compress the refrigerant or air, whatever may be. Then this condenser will transfer heat of high temperature. Then this the high pressure refrigerant will try to expand with the use of expansion valve, then we can have the low temperature refrigerant. So you know the principle of expansion. So this will give you the reduced temperature. Then this will pass through the evaporator. Then after that, so this is the cold portion, right? So this is the hot portion. The temperature of this portion will be more. Then the temperature of this will be less. Then this low temperature is transferred to the medium, to the system or refrigerator, right? So this is the actual vapor compression cycle. So we just know the components. Then this is the diagram, schematic diagram of line diagram of our VCR. So in that we are having compressor, then we can go with the 1 by 1 2 3 4. So this is the part. We have evaporator, then we have compressor, then we have condenser, then we have expansion device. So the upper part has the high pressure side, and the lower part has the low pressure side. So the pressure of this medium is low in this region. So in this region, below this region, the pressure is low. So after the exit of our compressor alone, we can get the high pressure. So this in this region at 0.3, the pressure is high, also temperature is high. Then this will subject to condensation process. Then this will allow to expansion device. So before entering the expansion device, the pressure is high. Right, so this is the line diagram of our vapor compression cycle. Then same diagram, but yes. So here we have compressor. The superheated vapor enters the compressor where its pressure is raised. So you know what is the principle of a compressor. So the superheated vapor. So the input of this compressor will be your superheated vapor because of evaporator. You know what is evaporator? This will be like a boiler, right? So the output of a evaporator will be superheated vapor. So this will subjected to compression with the use of compressor. Then we can have the evaporator, the low pressure liquid from the expansion device is in evaporator absorbs heat and changes to gas. So in this evaporator, so this low pressure refrigerant absorb heat that is inside the chamber. So if the temperature inside the chamber is high, we can get the that heat, latent heat, to get the refrigerant cold. Refrigerant changes to gas. So you know what is the evaporator. So this evaporator will take the latent heat of the system. Then we can have the condenser. So the high pressure superheated gas. So we know after the compression there is a high pressure superheated gas is cooled in several stages in the condenser. So you know this chiller will be involved here. So this superheated high pressure gas is cooled in several stages with the use of fins, right? So then you know what is the expansion device. So this superheated gas, then the high pressure gas, then the pressure will be reduced after this expansion device. Then this is the pH and TS diagram of our VCR system. So like our previous pH diagrams and TS diagram. So just you can refer this TS diagram, right? So we know this is saturation liquid line, this is saturation vapor line, then this is critical point. So in this case, this process, this 1 to 2, again this is isentropic process. Then 2 to 3 isothermal process, that is then again 3 to 4 is isentropic process. then 421 again isothermal process. In the case of pH diagram, so also we can have the same. This 1 to 2 is isentropic, then 2 to 3 is isobaric. So you can compare the isobaric and the isothermal is same here. So we can have isobaric process, then 3 to 4 isentropic again. So H and S will be same, right? So isentropic, then isobaric. So right, so there is 2 dash. We will look why this 2 dash happening. So the ideal refrigeration cycle graphed onto a pressure enthalpy chart is given here. So we can have a P and H diagram again. So the first process is isentropic, isobaric, that is evaporation process will give you a isobaric process. Then compression process will give you a isentropic process. Then this condensation process will give you a again isobaric process. Then this expansion device will give you a isentropic process. So in this region we can have the subcooled liquid, and beyond this line we can have the superheated vapor, then in between we can have the liquid vapor mixture. So the thing is we can get the refrigerant in all the 3 mediums. So because of that we will use the refrigerant, right? So then from this diagram we can identify. So this is the evaporator, this is compressor, then this is condenser, then we can have the expansion device. So in this process of evaporator, the states from 1 to 2 will happen, that is the entropy will get increase, but the pressure is constant pressure process. So the from the refrigerant is happening here, that is wet vapor condition will be here, right? So after the state 2, the process is compression process. So we know during compression process this gas, right? So this wet vapor get compressed. So in this superheater gas will be released. So also in this condensing process, condenser, the heat rejection to atmosphere will be happening. So we will use the coolant to get the heat transfer in this condenser, or or normal water may be used to get the heat transfer in condenser, right? So after the state 3 we can get the state 4. So that will be your subcooled liquid, right? So you can have the region in the subcooled liquid with after the exit of condenser. Then this subcooled liquid is passed through the expansion device. We can get again the wet vapor. Then the process is again cyclic process. So this will be a cyclic process. So we can classify the regions. So from 1 to 2 we can have the useful capacity of the refrigerator. Then in the region 4 to 3 or 3 to 4 we can classify that heat rejected in condenser region. Then we can have the regions in the H from 2 to 3 we can classify that motor input power. So here only we will do the input in the compressors. So we can have a region in is motor input power, right? So like that we can classify the vapor compression cycle. So here we will give the input, then here we can get the required output that we will see, right? So these are the components This diagrams we already discussed, already shown. So in this we have refrigerant, then evaporator, or namely chiller. So we know this chiller is an important part in this refrigeration. So the heat transfer will happening in this chiller or evaporator. So we need a heat transferring medium to get the heat transfer. Then we discuss a lot of compressor. Then we know what is condenser. Then this in some other cases this receiver may be attached with the refrigerator. Then this expansion valve, that is for your expansion device. So that will be our thermostatic expansion valve, right? So this is our expansion device. So we have all the components: compressor, condenser, evaporator, and expansion device. Right. So these are the components of our refrigeration system. That is the vapor compression refrigeration system. Then we can go with one by one. We know what is evaporator. So located in this space to be refrigerated cooling to be refrigerated. So that is inside the fridge. Then cooling coils act as an indirect heat exchanger. So there will be a cooling coils. Then this will absorb heat from surroundings and vaporize it. So because of that we can get the latent heat of vaporization and sensible heat of surroundings. So these two heats gets absorbed with the use of these evaporators. This is the diagram of evaporator tubing. So this will be inside your uh, component or system. So this will get evaporated. Then we can have the compressor. The superheated vapor enters as a low pressure, low temperature vapor and exits as a high pressure, high temperature vapor, that you know. So this increased temperature creates a differential temperature differential that will promote the heat transfer. So the increased temperature inside the compressor will create the temperature difference. Then because of that we can get the heat transfer. Then also there is increased pressure, so that will increase the saturation temperature of the refrigerant. So that will allows for a condensation at warmer temperature. So because of that increased pressure, we can get the condensation process. Then the increase in energy provides the driving force to circulate refrigerant through the system. Just we have to circulate the refrigerant through the cycle, right? So this increased pressure or increased energy will provide that circulation in the system. So we need pressure. Then we can have condenser. So the refrigerant rejects latent heat to cooling medium, you know, the chiller. The latent heat of condensation will be removed. The indirect heat exchanges may be used. The seawater, the example of indirect heat exchanger is seawater absorb the heat and recharge is overboard, right? So just the rain is happening because of this process. The seawater absorbs the heat and discharges overboard. So this is the indirect heat exchanger, but we have the heat exchanger, the different types of heat exchanger that will be discussed in the 5th unit. Just with the use of this heat exchanger, we can transfer heat in the condenser. The thing is, we have to transfer of latent heat from the system. Then the component receiver is attached here with temporary storage space and surge volume for this subcooled refrigerant. So in this region, the refrigerant will be in subcooled liquid stage. So because of that, we can have this receiver. So this serves as a vapor seal to prevent vapor from entering the expansion valve. So we have TXFV. So this expansion valve uh, to 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 get a peaceful function of these valves, we have this receiver in the system. Right, so we can have the TXV, that is the expansion device. So thermostatic expansion valve is used here. The liquid refrigerant enters the expansion valve at a high pressure and leaves at low pressure wet vapor. Right, so the input of the expansion valve is high pressure and the exit will be your low pressure wet vapor. So the vapor forms as the refrigerant enters saturation region. So because of that we need this TXV. So this will control the pressure reduction, then the amount of refrigerant entering evaporator. Evaporators controls capacity. So because of these two reasons, we need this TXV, that is your thermostatic expansion valve. So normally, so this freon refrigerant is used in our commercial refrigerator. So this TXV is used to get the expansion of this freon. Then this is the diagram of our TXV, thermostatic expansion valve. So in this there are a lot of components that we no need to discuss. Just know there is a diaphragm, there is a spring chamber, there is an outlet, there is an inlet. Then we can get the adjustment. Then we can have the port. Then we can have the valve steam, like that. Then we can have the thermal bulb. So the name itself, we can have the thermostatic expansion valve. Then because of this thermal bulb, we can control the temperature of the expansion valve. Right. So the thing is, just we will pass the subcooled liquid. Sorry. Yes. We will pass the refrigerant into the system that has high pressure and leaves with a low pressure wet vapor because of this valve, expansion valve. So this is the diagram. Then we can have the thermodynamics of our VCR. So from now we are going to look at what are the thermodynamics involved in this VCR, that is the vapor compression refrigeration cycle. So this is, so in this compressor part we need to give work. Then this is process 1 to 2. Then process 2 to 3 we can have the condenser, there is a heat transfer, that is Q out will be happening here. Then in this expansion valve we can get the high pressure to low pressure wet vapor. Then so at the state 4 there is a two-phase liquid vapor mixture will be happening. Then this two-phase liquid vapor mixture will subject it to evaporator. Then we can get the saturated or superheated vapor. Right. So we can compare with this to the TS diagram. So we can go the process one by one. So in this process 4 to 1, the two-phase liquid vapor mixture of refrigerant is evaporated through heat transfer from refrigerated space. Right. So this is the process 4 to 1. Then in the process 1 to 2, there is a vapor refrigerant is compressed to a relatively high temperature and pressure requiring work input we need to give, right? So this is the process 1 to 2. So then in process 2 to 3, the vapor refrigerant condenses to liquid through heat transfer to the cooling surrounding. So this is high temperature superheated vapor, right? So saturated or maybe superheated vapor. So this, if we subject this superheated vapor into condensation process, we can get the liquids, right? So this will happen in the process 2 to 3. Then in the process 3 to 4, there is a liquid refrigerant expands to evaporator pressure. So we need this TXV, the expansion valve. Then again we will get the liquid vapor mixture after the state 3, that is state 4. So again, this is a cyclic process. We can have the vapor compression refrigeration cycle as a repeating manner. Then the engineering models of this VCR, each component is analyzed as a control volume at a steady state. This we know what is the control volume and we know what is steady state. Then the dry compression is presumed here. Then the refrigerant is a vapor. These are the assumptions. Then the compressor operates adiabatically. Then the refrigerant expanding through the valve undergoes a throttling process. We know why we need TXVs. Then the kinetic and potential energy changes are ignored here. Then we can have the applying mass and energy rated balance as evaporator will be equal to this one. Right, then we can have the equation in the evaporated part, that is your heat transfer Q in by rate of mass transfer will be H1 minus H4, that is enthalpy minus change in enthalpy, right? So the heat and transfer will be change in enthalpy, that we know very well. So the evaporator is the process 421, so we can have this equation. Then the term Qn is referred as the refrigeration capacity. So this expressed in kilowatt in SI unit systems or BTU per H in the engaged system unit system. So normally we will use the SI unit here. So just know the units, kilowatts. And a common alternate unit is the ton of refrigeration, also will be used, that we discussed in the previous slides. So which equals to 200 BTU per minute, or about 211 kilojoule per minute. So that is the, if you want any unit conversion, we can use this. The thing is, Qn will be in kilowatts or maybe in tons of refrigeration. Then if we apply the mass and energy rate balance in compressor, so in compressor we know the process is adiabatic compression. Then we can get the W in by rate of change of mass will be H2 minus H1, again the change in entropy. Then in the common condenser, again we can have Q out by M as a change in entropy. Then also in expansion valve, throttling valve, here the Q will be 0, so we can have the H3 minus H4 is equal to 0. Then we can have the H3 will be equal to H4. Right, so enthalpy will be equal before and after the process of throttling. Right, so the performance parameters of our refrigerator can be classified by the use of, so COP will be output by input. So here Qin will be Qin by M dot will be your output, and W compressor dot will be W by M dot will be your output. Then we can have the equation. This is already have in the condenser part, then this is already have in your compressor part. Then we can simplify the equation as H1 minus H4 divided by H2 minus H1. Then if we simplify, then we can have the TC, compressor temperature, and there is then high temperature, low temperature, cold temperature, right? So this TC or TL, low temperature, then this TH will be high temperature. Right, so the COP of our refrigerator is the low temperature, or maybe QL divided by QH minus QL, or if in the case of temperature we can use this formula, that is the TL divided by TH minus TL, that is high temperature, low temperature. So this first formula will be in the form of COP. Then also the Carnot efficient of performance, we know what is Carnot cycle. So mainly in Carnot cycle, the heat transfer will be equal to the temperature difference, right? So they can use the temperatures alone. Then the equation represents the maximum theoretical coefficient of performance of any refrigerant cycle operating between cold and hot regions at a temperature region, that is TH and TL respectively. So we can use the COPs in the form of both the COP, also in Carnot coefficient of performance. So with these equations, just we can try to solve this problem. So here the refrigerant 134A is used as a working fluid. Just to go through the problem, then try to solve the problem. Just look at the problem 2 to 3 times, then we can get the idea about how to solve the problem. Right. So the refrigerant 134 is a working fluid in an ideal compression refrigeration cycle. The refrigerant leaves the evaporator at a minus 20 degrees Celsius. So the exit temperature of evaporator is given, that minus 20 degrees Celsius. Has a condenser pressure of 0.9 megapascal. So they gave the condenser pressure. Then the mass flow rate also given, that is 3 kg per minute. Then we can have the just these data alone we are having. So we have a temperature, and we have a pressure, then we have a m dot. Then we need to find the COP of refrigerant, also COP of refrigerant for Carnot for the same T max and the T minimum and the tons of refrigeration. Right, so these are the data given. The thing is, we need to find the COPs for both refrigerator and Carnot. Right, so we have the formula, also we have the details, we have the given data, then we can try to solve the problem. So using refrigerant 134A, just we can refer the data. So like our normal steam tables and properties of just if you refer the property tables and chart, we can get the properties of refrigerant 134A. So that we discussed a lot in the previous units. Just you can refer that. So the compression inlet, the temperature is given, T1 is given. So we know the inlet of this compressor will be saturated vapor. So because of that, we can have the XS1. So just you can refer the TS diagram. So in that we will pass the saturated vapor to get compressed in the compressor. So because that, we can get the assumption of X as 1, then we have T as minus 20. Just if you refer the temperature table, just we can have the H1 value and S1 value. Just we can directly take the HF and SF values from the property tables and charts. Then the state 2, the compressor X6 will happen. The pressure is given there, so 0.9 megapascal, that is 900 kilopascal is given. Then we have the S will be equal, right? S1 and S2 will be equal. So because of that, we can directly take the S values. So we have right. So we have P2, P value and S value. So based on that, we can take H value and T2 value in the property tables and chart. Then so we have the pressure after the exit pressure is given. So the state 3 pressure will be same, right? So yes, this is the condenser exit pressure. So the pressure won't be changed in the condenser process. So we can have the P2 is equal to P3. So we can have P3 as a 0.9 megapascal. So also in this state P3, that will be your saturated liquid, right? So the state of this refrigerant will be saturated liquid. So in that we don't have the X value. So the X value will be 0. So if you refer that pressure table, just we can have the H3 value and S3 value from the tables and chart. Just you can refer that. If you have any doubts, you can ask at any time. Right. So the thing is the same. Just you have to refer the property tables and chart on refrigerant 134A table. Right. So we can get the details. So at state 4 there is a throttle exit, so the temperature will be equal, so we can have the temperature as T4 and T1 will be minus 20 degrees Celsius. Then also the H value will be equal, so we can have the H3 is equal to H4 is equal to H3. Then so based on this we can found this X4 value. Right, so in this state the refrigerant will be in mixture form, right? There is a liquid, also there is a vapor, so we have to found the X value, this quality value. So the quality will be 35% or 36%. So we need to found this X based on this H3 and H4 values. So we know H3 value, and we can take that H4 value from the table corresponding to the minus 20 degrees Celsius, and if you compare both we can get the X4 value, then also we can get the S4 value. Right, so with the use of this refrigerant table we can get the properties, other properties also. Then we can use that properties to get the COPs of refrigerant, also the COP of refrigerant of Carnot cycle. So we need a COP of refrigerant in the form of H. So we know we found H1, we found H2, we found H4. So if you substitute in this equation, then we can able to found the COP value. So we can see this, right? So you can see there is COP is 3.44. So normally our efficiency will be in percentage, that will be less than 1, less than unity. So where in the case of COP will be more than 1. So here in this system we have COP 3.44. Then the tons of refrigeration is often called cooling load or refrigeration effect, may be calculated with this equation. QL, heat loss, heat transfer loss will be H1 minus H4, that is from the first equation. Then we gave the m dot value, then we have H1 value, then we have H4 value, then we can able to found the QL value. So that is QL will be this value, right? Yes. So we need to found all the three, right? Tons of refrigeration. Right, so we need to found this QL. So that will be around 1.94 ton. Then the COP of refrigerant for Carnot will be TL divided by change in temperature. So that will be minus 20. We have the values, right? So we have T low temperature will be minus 20 degree and high temperature will be 43 degrees Celsius. Just you can compare. In this we have temperature minus 20. We have this temperature 43.79. So also we have T4 minus 20 degrees. So here we have the low temperature will be minus 20 and high temperature will be 43.79 degrees Celsius. So with the use of these two, we can calculate the COP of Carnot. Then that will be equal to 3.97. So right, so this is approximately equal to the COP of refrigeration. Right, so with this manner we can solve the problems involving in the refrigeration cycle. So the another measure of the effectiveness of the refrigeration cycle is how much input power to the compressor in horsepower is required for each tons of cooling, also possible the unit conversion is 4.715 HP in terms of cooling. So we can convert the tons of cooling into horsepower, so that we no need. If they ask, we can try to solve this. So we can convert. So just 4.715 divided by COP refrigerant will give you the W net by QL. So that will be approximately 1.37 by 37 HP per ton. That means horsepower per ton, that we no need. If they ask, you can found. Then these are the features of actual vapor compression cycle. Then the heat transfer between refrigerant and cold and warm regions are not reversible, so that we know very well. So heat transfer between the refrigerants and cold and warm regions are not reversible, that you know. Right. So the temperature of warm region is above the region, then the temperature of cold region will be below the region, and this won't be reversible. Then the refrigeration temperature in the evaporator is less than the low temperature. Right. So this will be the region if, and this will be the region of these two. Then at this state, the temperature will be less than the low temperature. Right. Just we can compare. So in the process 4 to 1, we can have the temperature less than the low temperature of the refrigerator. Then the refrigerant temperature in the condenser is greater than the TH. So if this is the region of high temperature region, then the condenser will be taken in this place. So the temperature of the refrigerant is greater than this TH. And the irreversible heat transfer have a negative effect on the performance. So we know, right? So irreversible heat transfer. So the refrigerant should have a reversible heat transfer. Right. So the COP decreases primarily due to increasing compression work input as the temperature of the refrigerant passing through the evaporator is reduced relative to the temperature of the cold region. Right. So just we are transferring heat from temperature of cold region to the temperature of warm region. Just we can refer. Right. So this will decrease the COP of our refrigerator. Just again I was saying. So this reduction. Right. The temperature of the refrigerant passing through the evaporator is reduced relative to the temperature of a cold region. Then the temperature of the refrigerant passing through the condenser is increased relative to the temperature of the warm region, so upper parts. Right. So we can get the increased refrigerant temperature. Also, we can get the decreased refrigeration temperature based on the selection of our refrigerant. Then the irreversibility during the compression process are adjusted by dashed lines from state 1 to 2. So these dashed lines will give you the irreversibility. You know what is reversibility and irreversibility, right? So we can have the irreversibility with the dotted lines, dashed lines. Then the increase in specific entropy accompanies the as an adiabatic irreversible compression process. This process 1 to 2, that is irreversible adiabatic process, but we can have the 1 to 2s instead. So this will greater than our counterpart isentropic compression process. So this is actual the isentropic process, but for our assumptions we are having this 1 to 2s. So that will be our isentropic compression. Then since the process 4 to 1 and thus the refrigeration capacity is the same for cycle 1, 2, 3, 4, 1. So this the actual lines 1, 2, that is dashed lines, then 3, then again dashed lines, and 1, 2s, 3, 4, 1. This 1, 2s, 3, 4, 1 is same. The cycle 1, 2, 3, 4, 1 has the lower COP. Right, so just we can have the 4 to 1. Just we can compare the process 4 to 1. So in both the case we can have the same process at 4 to 1. So because of that we can have the temperature is identified here, right? So the thing is we can have the equals lower COP compared with these two. Then the isentropic compressor efficiency is the ratio of a minimum theoretical work input to the actual work input each per unit mass of flowing. So we can have the isentropic compressor efficiency. So this is isentropic compressor efficiency. We can calculate the efficiency of the compressor. So input divided by output, right? So here we can have the given input as H2s minus H1. So that will be your given input. Then output will be output will be H2s. So this is your actual output, and actually we gave this input 1 to 2, right? So H2 minus H1 will be input. Then this H2s minus H1 will be your output. So because of these two, we can calculate the thermal efficiency of the compressor part alone. Then the work required in this isentropic compression from compressor inlet state to the exit pressure is gives the compressor efficiency. The denominator gives the work required in an actual compression from compressor inlet state to exit pressure, that we know very well. So just we can refer this. So this is our actual. Then this is our obtained. So based on that, we can solve this. We can try to solve this example. So example of the table provides steady state operating data for the vapor compression refrigeration cycle using R134A refrigerant as the working fluid. For the refrigerant, mass flow rate is 0.08 kg per second. So we have to determine the compressor power, then refrigeration capacity in terms of cooling, then coefficient of performance, then isentropic compressor efficiency. So these are the given data. So they gave H1, H2, H3, H4, also H2s values. Then we need to found the, also they gave m dot, that is 0.08 kgs. Just we need to found the compressor power. So we can calculate, we have the formula compressor power as m dot H2 minus H1. Just we can directly use the given data to get the compressor power. That will be in kilowatts, that you know, it will be approximately 3.1 kilowatts. Then second, we have to calculate the refrigeration capacity. We can use this formula, that is Qn in the condenser part. Then we have the m dot values, then we have the H1 value, then we can have the H4 value. Just if you substitute, we can get the Qn. Will be in tons of cooling. Then the third, we need to find the COP. So we know the formula, that is H1 minus H4 by H2 minus H1. So we know the values, just we can directly substitute, get the COP of refrigeration. That will be 0.86. Then The fourth, we need to find the isentropic compression efficiency, that we know the formula, that is H2S minus H1 divided by H2 minus H1. Yes. So just we can the data is given, right? So the data were given. So just we can directly substitute to get the isentropic compression efficiency. So that will be approximately 80%. That is 0.8. So again, this pH diagram will give you the thermodynamic property diagram commonly used in the refrigeration field. So here, like our property pure substances, we have the refrigeration, it is subcooled liquid, then superheated vapor. So before the subcooled liquid region, we can have the saturated liquid region, we can have the subcooled liquid. Then this saturated vapor region, beyond the saturated vapor region, we can have the superheated vapor. So if that is the case, we can have the constant enthalpy for superheated vapor. Then so these lines will give you the constant temperatures. Then process 4 to 1 will decide the evaporator pressure. Then process 2 to 3 will give you the condenser pressure. This actually we already discussed this pH diagram. This just to compare the pressure and enthalpy of our refrigeration cycle. Just we can again refer this. Then there is other refrigeration cycles also possible. Just we can have the cascade refrigeration system, that is very low temperatures can be achieved by operating 2 or more vapor compression systems in series called cascading. Just we have the two refrigeration system in series. Yes, this will be one refrigeration system, and this again one refrigeration system. Like our regenerator cycle, just we have this cascade refrigeration system. So to get the improved COP, so this cascade is using. So the COP of refrigeration system also increases as the results of cascading. So just we can use this. So if any two refrigerators is connected with the series, just we can get the increased COP. So that also possible. So that will be called under the name cascade refrigeration system. So this will give you the TS diagram of our cascade refrigeration system. Okay, just you can refer this. Just there is one, again there is two, second one, and then this portion is a decrease in compressor work. So we can get the decreased compressor work, also get the increased COP with the use of this cascade refrigeration system. Then there is a multi-stage compression refrigeration system possible to get the increased COP. So this flash chamber, then so here we introduced two expansion valves here, right? So because of that also we can get the increased COP. So this is called a multi-stage compression refrigeration system. So here just there is two expansion valves. Also there is a flash chamber. So because of these two, we can get the increased temperature. Sorry, increased COP. Then there is a multi-purpose refrigeration system with the yes, here also there is expansion valves, but there is alternative path also provided. So you can compare these two. Will be same, but yes, you can compare the slide number 59 and slide number 58. Both will be same, but the changes in the expansion valve will be the matter. So we can have the refrigerator inside these in between these two expansion valve, means we can get these kinds of TS diagram, that will also give the improved COP. So in this case, the refrigerator with a single compressor can provide refrigeration at several temperatures by throttling the refrigerant in stages. So here we provide the refrigerator, so that will give you the several temperatures by throttling the refrigerant. So in this stage, so this refrigerator will give you these stages. So depending on our requirement, we can get the expanded gas. Also, the liquefaction of gases is possible with the use of this regenerator. So another way to improve the performance of vapor compression refrigeration system is by using multi-stage compression with regenerative cooling, also possible. Just go through the diagram and TS diagram of these alternate methods of refrigeration. So here we have regenerator. Here we have regenerator. Then we have the expansion device. Then just this condenser part, right? So the circuit diagram will be differ, but the thing is we have to increase the COP of the refrigerator, right? So liquefaction of gases also possible with the use of this regenerator. So we know what is the regenerator, how it performs. So regenerator, in the sense, the heat transfer will be used to regenerate the system, right? So these are some alternate methods of refrigeration. Just go through this. So that's enough. So the second type is vapor absorption refrigeration system. So that can be discussed in the next class. So with this, we can conclude today's class. So just in our refrigeration, we have different types. So the first type is VCR, that is vapor compression refrigeration system. So with this vapor compression refrigeration system, we have the different components like compressor, condenser, operator, and expansion valve. So with this, we can control the COP of refrigerator. Also, we can able to produce the refrigeration effect. Right. So the thing is, we need to transfer heat of low temperature. Already the surrounding temperature is higher than the low temperature of the system, right? So we can look the vapor absorption refrigeration type in the next class. So do you have any doubt in this VCR system? Just we can ask now, or else we can hang up. Thank you.
Sir?
Yes, ma'am.
Sir?
Yes, yes.
Sir, assignment due date கொஞ்சம் explain பண்ணுங்க சார்.
அசைன்மெண்ட் அம்மா?
ஆமா சார்.
டேட் 23
ஆயுத பூஜை வச்சுக்கிறோம்.
நெக்ஸ்ட் வீக் ஓகே. அந்த ஹாலிடேஸ் முடிச்சுட்டு சப்மிட் பண்ணிடுறீங்களா? வெனஸ்டே அன்னைக்கு 23, 26, 26, 27, 28 ஓகேவா? 28 நமக்கு கிளாஸ் இருக்கு 3, 4. 28 வந்து வெனஸ்டே வரும். ஸோ வெனஸ்டே ஓகே. அவங்க லீவ் உனக்கு வரும் இல்லையா? அந்த லீவில் கம்ப்ளீட் பண்ணுற மாதிரி பார்த்துக்கணும். ஓகேவா? ஸோ யுவர் அசைன்மெண்ட் ஷுட் பி ஃபுல்லி ஹேண்ட் ரிட்டன். ஸோ வி ஹாவ் டைம் டு டிஸ்கஸ் தி யூனிட் 5, but before that you have to submit your assignment. So that will be taken for your assessment 2 marks.
Okay.
Right. Okay.
Thank you, sir.
Okay, ma.
Thank you.
Okay, okay, ma. Okay, ma.